All right, so let's take a look at the speed at which waves travel. How fast do these things get around, and how do we calculate it? So it's very simple. Turns out that there is a wave equation that gives you exactly that. The velocity of any wave is equal to its frequency times its wavelength. Okay? And so let's just make sure the units work out here. We know that velocity must be meters per second, right? Frequency is waves per second. So that unit is actually inverse seconds, or 1 over seconds. Okay? And wavelength is a length. It's a distance, which is SI unit meters. Right? So that is indeed meters per second equals meters per second. Okay? So it's important to know that this relationship, velocity equals frequency times wavelength, is universal. This is a universal relationship. It doesn't matter if it's a transverse wave, a longitudinal wave, a sound wave, a light wave, whatever it is, this relationship always works. Okay? And before we begin to explore how we might use it, it's important to know a few main speeds of sound and light. Okay, so the speed of sound in air at standard temperature and pressure is 373 meters per second. Okay? The speed of light in a vacuum is 3 times 10 to the 8 meters per second. That's astronomically, preposterously fast. Okay? This explains why if you see an airplane traveling, right, you see the airplane over here, but it sounds like it's coming from over here, right? That's because the light hits your eyes almost instantaneously, but it takes a little bit of time for the sound. So when airplane's over here, the sound that it was giving off over here is just reaching your ears then. All right? It's kind of interesting. Now, how astronomically fast is the speed of light? Well, that converts to 180,000 miles per second. 180,000 miles per second. That means if I'm at a rock concert and I flick my lighter or turn my cell phone on, right? That means that light will whip around the Earth 7 times in 1 second. All right? That's fast. And astronomically speaking, it's kind of really slow. So for example, if we wanted to send a text message, and text messages are microwaves. Okay, so they're going to also travel at the speed of light. All electromagnetic radiation travels at the same speed. If I want to send a text message to the nearest star, and which is Alpha Centauri, and it is 4 light years away, that means that it's going to take 4 years for that light, those microwaves, to travel to that star, and another 4 years for it to come back. That's preposterous. And it's very depressing for anyone who is excited about the possibility of actually being able to communicate with and interact with extraterrestrial life, which must be out there, right? Because it's a really, really big universe. But even if we're talking to life on our nearest star system, it would take 8 years to send a text and get a response back to you. Okay? Sorry to bum you guys out. So those are the speeds of sound and light. So now that we know that, let's look at some problems. How can we use this equation to solve for something interesting? Okay? So if you go to the slide that says the speed of sound waves, it says Lady Gaga is known for having perfect pitch. Very impressive. Very few people have it. It's the skill of being able to sing any note without using a piano to get the frequency first. I don't have that, and I've been a musician since I was 13 years old. So if Gaga sings a perfect middle C, which is 261 hertz, what is the wavelength of the sound wave leaving her mouth? Okay. Well, we know, my friends, that we have this equation, that V equals frequency times wavelength. And this applies to sound as well as it does to light, right? And so we know that sound has a velocity of, we just talked about it, 373 meters per second in air at standard temperature and pressure. And we know that this frequency is 261 hertz, right? Which makes it very, very easy to find the wavelength of such a light. We simply do the division, We find that the wavelength of that sound is 1.4 meters. There you go. There you have it. It's pretty long, right? Most of you probably think sound waves must be real, real little. Well, the wavelength of that middle C is actually 1.4 meters, all right? Next question, part B. If she is in a 100-meter wide stadium and says, "Hello, San Diego," "Hello, San Diego," and she gets that echo, how long would it take for her to hear that echo? All right. Well, we know that velocity equals frequency times wavelength, right? But we also know that velocity is equal to distance divided by time. In here, we're trying to find a time, right? The time in which she hears the echo. So t equals distance divided by velocity, right? But the distance the sound travels is from one side of the stadium to the other side of the stadium because it's an echo, right? It's going there and back to hit your ears. So that's going to be twice the length of the auditorium, which is 100 meters wide. So 2 times 100 meters. Again, divided by the velocity of sound, which is 373 meters per second, right? And so the time that it's going to take to hear that echo is, I get a half a second, 0.53. So it'll be really quick. It'll be like one of those kind of more slappy echoes, right? "Hello, San Diego. Hello, San Diego." Make sense? All right. Now, one thing you need to know, if you guys could go to the next slide, sound waves need a medium or material to travel through, okay? Because what is sound? Sound is you're actually causing a disturbance to a medium like the gas in the air, or, you know, if you hear a sound through wood, you're actually shaking wood molecules, right? And they're bouncing against each other, and you have these compressions, and it's called a rarefaction, where it's less dense for a moment, right? And that propagates throughout the material. And so that means that the speed of sound is not going to be the same in every material. So if you guys could look at this chart here, you could see how the speed of sound can change dramatically from one material to another. In air, as I've said, at standard temperature and pressure, it's in the high 300s, whereas in a solid like steel, it's 5,960 meters per second, much faster, many times faster. So know that, be aware of that the speed of sound really depends on what medium you're immersed in, and it's going to vary dramatically.